So far, when we've looked at differentiating functions, we've always assumed that the function can be written in the form y equals f of x. Very often this isn't the case. In such a situation, an equation can be given in what's known as an implicit form rather than an explicit form. For example, we've seen this already with the circle, which is given by x squared plus y squared equals r squared. In order to write this curve in terms of functions, we need to write a separate function for the top half and for the bottom half. That is, for the top half, we need to write, while for the bottom half, we take the other route when solving for y. Those two functions produce a curve which is a circle, x squared plus y squared equals r squared. This is an example of an implicit equation. How do we go about finding the derivative of functions like this? One way to do this is to take y1 and y2, differentiate them, and find the derivative that way in patches. Let's try that. Let's start with the top half. Using the chain rule, I get 1 over 2 times the square root of r squared minus x squared, all multiplied by minus 2x. And this, I notice, is just minus x over y1. Similarly, if I do it for the bottom half of the curve, I find I have minus. This comes out to be minus x over y2. So for the top half and the bottom half, the derivative is the same in terms of x and y. Is there an easier way to find this? The answer is yes, and we use implicit differentiation to find this. We start from the equation for the circle, which is x squared plus y squared equals r squared in implicit form, and we differentiate that term by term. We calculate d by dx of each term. So with an equation, as long as I apply the same procedure to each term, it's a valid operation. Now what do these become? Derivative of x squared is 2x. The derivative of y squared is where we need to be careful, because we must remember that y depends implicitly on x. So we differentiate this using the chain rule. And for the term on the right hand side, well, r is a constant, which is the radius of a circle, and that's just equal to 0 when we differentiate it. So if I take this equation then and rewrite it for dy by dx, I find just minus x over y, which is what I found when I used the explicit forms of the curve. So implicit differentiation then is a very quick way to find derivatives of implicit functions. And let's just have a look at some examples of implicit functions to see how complicated things can get. If I have a cubic relation between x and y, I can end up with curves which have loops in them, like this example. If I take curves where cosines and sines and oscillating functions are involved, things can get very involved indeed. So here's an example which looks relatively simple when written down, x cos y plus y cos x equals 0, but a plot of this shows that it's quite a complicated family of curves. As a final example, let's look at something else which also looks relatively straightforward. As an equation, sine of x squared plus y squared equals cos xy. A plot of this reveals an extremely complicated mixture of curves, lots of ellipses at different angles. So to try and find the derivative of those by splitting it up into separate functions would be extremely complicated. Implicit differentiation solves this problem. Let's just try a simple example. Sine xy equals y. In this example, it's impossible to write y as a function of x. So implicit differentiation is the only way to solve a problem like this. So what we do is we'd find d by dx of each term. The derivative of sine x times y, using the chain rule cos xy, times the derivative of the part inside the cosine, and that is y plus x times y prime. And now if I differentiate the right hand side, this is equal to y prime, where I'm using y prime as a shorthand for dy by dx as usual. Now we see we've got y prime on both sides of the equation. So what we do is we try and isolate y prime, and you can usually do that using implicit differentiation. So what I'm going to do is gather all the terms with the y prime on the left hand side and all the terms without on the right, and then all I need to do is solve for y prime, and I'll rewrite it as dy by dx. And this note tells me the derivative now, where the derivative tells me at points on the curve with x and y values given by my original equation, which is sine xy equals y, tells me what the derivative is there. Note that when the denominator goes to 0, the result will often be infinite, which means that we have a vertical line at that point.